So the next talk will be by Barbara Terhal from TU Delft, and she will talk about quantum error correction.
Yes, I'm very glad to be here. A nice conference, very broad set of topics, which everybody can learn a bit. And so I'm here to talk about quantum error correction. I'm not going to go back 100 years, because we didn't have quantum error correction. But I do like to say something about the history of quantum error correction. And last year, as you've already heard maybe from a few talks, last year's been a very good year for quantum error correction. So I may also mention some of the experimental results, but only very briefly, because what I want to focus on is a little bit the theory. And before I do that, I have one little sort of visual intro. This is a lithograph by Escher. He's a Dutch artist in the past, made in 1950. And the title of this is Order and Chaos. And I'm sure you understand what is the chaos and what is the order here. It's quite pretty. And of course, you could say, and this is sort of the theme of my talk, we're starting from chaos, we're starting from noisy qubits. Although, if you hear the talks here, there's been a lot of progress in making these qubits function better and having good control over them. But if we ask, we want to build a computer, we want to have a control that's, which error rates are 10 to minus 20 or something like that, right? And that's hard to achieve just pure physically. So we start with chaos or disorder, and we want to make something ordered. And actually, I like this picture also because there's a nice code that I've studied that I just want to flash by, which relates to a figure called the small stellated dodecahedron. And what Escher is drawing here is a small stellated dodecahedron. Like in the hall here, you have another polyhedron hanging, which has trivial topology because it has the topology of a sphere. And the dodecahedron, as you know, is also one of the Platonic solids. It also has the topology of a sphere. You can stellate it, meaning that from the dodecahedron, you kind of extend the edges. You get the small stellated dodecahedron. And it was surprising to people in the past that this has non-trivial genus. So topologically, this is actually an interesting object. It's actually, you can see it, although you can't see it. It has a topology of a torus with 4 holes in it, so a 4-handled torus. And because of that, and because there's a relation between topology and error correction that I'll come to, this figure can encode 8 logical qubits. So we put physical qubits on its edges, if anybody is ever going to make this. So there are 30 physical qubits on its edges, and this represents 8 logical qubits. I'll tell you what logical qubits are, and it's able to correct a single error. And I've had some bachelor students actually do fun projects on this to design, how you do error correction. And at some point in the future, I hope that somebody will do an experiment on this. Okay, but that's just sort of an idea. And here's some other local order and maybe chaos. So I'm spending 3 months, maybe you've heard, at the IIT Madras, which is a very interesting environment. And I see things like extremely pretty ordered structures. And I see them also next to, structures that you hope, we can clean up in the future. David, my husband, is in the local neighborhood where we live. He actually picks up trash, random trash from the streets to help create order. It's not what he's going to win the Nobel Prize for, but it's a good, contribution to the community. All right, so that's the goal. But now let's go back in time. So let's go back to 95, 96, and I think, Peter Toller already mentioned 94 is the time where Shor invented his factoring algorithm, and then right away there was a discussion of like, well, great, now we really want to build this quantum computer, but how do we do this? And I think quantum error correction is sort of a fundamental discovery, and that's the point I want to make. And I want to make this point based on just actually quoting 2 people who were involved in this discovery, namely Andrew Steen, who is a professor at Oxford, and Peter Shor. And so Andrew Steen, as I'm just quoting from this paper in 96, actually the first error correction code was by Shor in 95, but here's Steen in 96. However, it can be argued that the possibility of decoherence is itself just as fundamental a feature of quantum mechanics as the interference and entanglement on which a quantum computer takes its advantage. Such decoherence must be considered, for example, in any discussion of Schrodinger's cat paradox. The cat in Schrodinger's thought experiment corresponds here to the quantum computer itself. Hence, the idealization in which decoherence is taken to be negligible is not merely a limit on the practical application of the theory of quantum computing. It's in fact an idealization too far, since it involves neglecting a basic aspect of quantum theory as been emphasized by Lauendauer. Right? So he makes the point that you cannot think about a quantum computer if you're not thinking about noise. And I think this is a very fundamental point of view, because it could have been that there were no quantum error correction codes, or there was no theory of quantum fault tolerance, or we would be still, we would be exponentially have such difficulty making progress in this, and there's a fundamental law that says this is not possible, right? Because it's so in some sense, I would say the things that we do in quantum error correction are the Schrödinger cats. We're making the Schrödinger cats of today, in the sense that what we want to do with quantum error correction is that we add redundancy, so our quantum information is carried by more degrees of freedom, and this usually means that I'm more prone to errors, I'm more prone to decoherence, I'm more likely to have to describe my system as a classical system. I'm making the transition to the classical world. But no, instead, by actually doing quantum error correction, by monitoring for errors, we are building something that behaves quantum mechanically, even though it's macroscopic. And by macroscopic, we don't mean that it has to be large in size, like a big mass or something. It is carried by many degrees of freedom. The information is carried by many degrees of freedom. These degrees of freedom at some point can relate to mass of a system, of course, but that's not our primary goal. All right, so that's Steen. And then Shor, so this is actually earlier, Shor wrote down the first quantum error correction code, and I want to explain a little bit how this works, but I also want to quote from his paper, which is 95, because this is the essential idea. So you'd think that decoherence is something irreversible, right? This is how it's presented. Like we look at a system and we collapse the wave function. Measurement destroys the information. This is different from classical. This is the fundamental departure from classical information. And the insight of Shor was that one can reverse decoherence. One can reverse measurements of some, except, well, then you have to be careful what he's saying. So to preserve the state of the superposition of the encoded qubit, what we do in effect is to measure the decoherence without measuring the state of the qubits. All right, how do we do this? Well, the reason we can do this is that we expand 1 qubit to 9 qubits. So we want to preserve 1 qubit. We're going to represent it as states of 9 qubits. So much larger space. And so that much larger space means that we provide some sort of redundancy. Right? This also says it's inefficient. We need now 9 qubits to represent 1 physical qubit. And that 9 qubits we all have to control very well. So this is some overhead. All right, but this is inevitable. Okay, so our encoding scheme scores information in the entanglement between qubits so that no information is stored in any one specific qubit. Measuring any one of the qubits gives no information about the encoded state. Right? So if I just, observe 1 qubit, that state of whatever I measure is independent of the globally encoded information. And that is important because we expect that errors are more likely to affect just 1 qubit or maybe 2 qubits, but not all 9 at the same time. This is a fundamental assumption about physics and about locality of errors that underpins quantum error correction. Okay, so essentially what we're doing is putting all the information in the signal into dimensions of the signal space that are unlikely to be affected by decoherence. We can then measure the effect of the decoherence in the other dimensions of the space, which contain no information about our signal, and use this measurement to restore the original signal. All right, so that's just in words, right? So we don't want to measure the logical information, like what state my qubit that I'm encoding is in. Is it in a 0, is it in a 1, or something in between? That I don't want to get any information about. What I do want to measure is what error has happened on any of these 9 qubits, or has any error happened on these 9 qubits? Okay, so here, so if we describe logical informations mathematically, we usually put bars on these things. So for example, here you see plus with a bar over it. the plus state usually is a superposition of 0 and 1, and the bar just means this is a logical qubit, right? So don't read this state is actually just some particular state of 9 qubits. And the minus state, which also has a bar on it, is some other states. These states are orthogonal. And what you see here is that if you just look at this little group of 3 qubits, it looks like sort of a repetition code, in the sense that if one of these qubits were to flip, say there's an X flip on one of these qubits, I could just ask the system, I could ask these 3 qubits, oh, qubit number 1 and 2, are you the same bits? Are you both 0 or 1, or not the same, right? So I'm not asking every qubit whether you're 0 or 1. I'm just asking, are you both qubits the same, or are you not the same? So I'm asking about the parity of those 2 qubits. Yeah, this is the essential point. And I can do that the same for the, qubit number 2 and 3, and I can do that for these qubits. And if I ask that, are these qubits the same or not the same, I will be detecting whether there have been X errors, where there have been bit flips, right? So I can do that for all these triples and also for this word. And so basically what this says mathematically is that these states are eigenstates of so-called parity check operators. And these parity check operators you also have for classical codes. They say the parity of that subset of qubits must be 0, and then if I have a bit flip, then the parity flips, and that's how I detect an error. All right, fine, good enough. But in quantum information, and this is the essential departure of quantum error correction versus classical error correction, you don't only have bit flips, but you also have phase flips. And phase flips is a poly Z operator, say on a single qubit. On 0, it maps it to 0. On 1, it maps it to -1. Well, that minus, you never see any classical information, just a bit. But of course, if you have a state like this, whether you have a plus or a minus matters. Right? So you can say, well, what happens when I have a Z error, say, on this qubit, for these 2 states? Then you see that this flips, a single Z error will flip, these 3 qubits to these 3 qubits, but these will still be the same. And so what you can do is you can actually measure these operators, which are also parity check operators. And you can see, for example, that if I apply x1, x2, x3, this type of state with the plus is a +1 eigenstate. Whereas this type of state with a minus is a -1 eigenstate. Because if I flip all these 3 qubits, I get 1, 1, 1. And I flip all the 3 qubits here, I get 0, 0, 0. So then there's an overall minus sign difference. Right? So if I have a single qubit Z error here, so it flips this to the minus, and I do all these x's here, so on all here, then I'll get I'll get a minus sign. All right. So maybe if you're not following this in practice, in detail, the idea is that this code that Shor wrote down can correct any single error. So if any single error happens on those qubits, I can measure these parity checks. And so if there's no error, these are +1 eigenstates of these parity checks. And if there's a single error, they are, some of these parity check eigenvalues will be -1. And which one will be -1 will allow me to tell where the error happened, and therefore I can correct it, right? I detect the error. And this can happen for both, both if I have an X error or a Z flip error. And the important thing is that if I measure these parity checks, and that's the essential act of doing error correction, I'm not learning anything, I'm not distinguishing these states at all. In no way are these states distinguished by, because they all have, eigenvalues are all +1, they're not distinguished. All right, but there's another thing so the theory builds up a little bit more. So there are the parity check operators that we always specify when we talk about our error correction code. And then there's also something called the logical operators, which are just the operators that map like plus onto minus or 0 onto 1. And for example, you can ask, how do I get from plus to minus? Well, I can do, for example, Z1, actually Z4, sorry, Z1, Z4, Z7 maps me on from plus to minus. And so I can also ask how I can get from 0 to 1, and I can also do this with some bit flips. And so just to set this, introduce some language, these logical operators, they act on a bunch of qubits. And if the environment or if the noise implements that operator, well, there'll be no error because, for example, we start in plus and then where we won't detect any error, we map onto minus. And they're both +1 eigenstates of these parity checks, so we won't see a difference, but our logical information is changed. But these are more global operators because they act on 3 qubits. So the protection is the following, that the errors that actually happen are more likely to occur on a single qubit at a time. And it's unlikely that all of a sudden we'll have 3 errors at a time. That's the basis of the protection. And we call, so the distance of a code is the minimum number of qubits on which these logical operators act. So the distance in this case is 3 because the logical Z acts on 3 qubits and the logical X acts on 3 qubits. And it's known that the code can correct a number of errors, which is sort of slightly halved in the distance. Okay, so that was a little bit of sort of introductions. In order to specify a code, we specify parity checks, and we have to measure the eigenvalues of these checks, and we specify logical operators. And with the logical operators, we can specify the distance and also how many errors we can correct in principle. All right, now coming back to Steen. So Steen's code, so this was Shor's code. There's been generalization of Shor's code, but a more interesting code, perhaps also for what comes, is the code that Anders Steen introduced, because it also corrects any one error on the 7 qubits. He had a code that encodes 1 logical qubits into 7. And so these are the 7 qubits. 1, 2, 3, 4, 5, 6, 7. And now I have to specify the parity checks. So for every phase, for example, for this phase 1, 2, 3, 4, there is an all Z check. So, this could be all zeros or all ones or 0, 0, 1, 1, where the number of ones always must be even in order to be a +1 eigenstate of this Z thing. And similarly, I have an all X checks. That's not so easy to sort of say in this parity language. Okay, and then for every this phase, I have similar all Z's and all X's. So the parity checks are 2 per phase. So this is a code which encodes 1 logical qubit, and one could correct 1 error on any physical qubits. And its distance is 3 because the logical operator is an operator that can run around, like, for example, 5, 6, 7. So X, X, X is a logical X operator. Okay, why is Steen code interesting? Well, it's a nice little code, so interesting for small experiments, as we've seen them in the last few years. But it's also the smallest of a family of codes, which was introduced later by Bombin. And these are called 2D color codes. And you already see there's some coloration scheme. And these codes are all, the 2-dimensionals at least. They're a 2-dimensional lattice. And the qubits are the vertices of this lattice. And this lattice is trivalent, which means that every vertex has 3 edges coming out. And it's 3-colorable, right? So here, red, blue, and green. So 2 colors, you can't have any 2 faces with the same color next to each other. And for example, here you see sort of a bigger version of this little code. This is a next size up color code, because these color codes, they have some specific boundary. They're called triangular color codes. Here, there are some errors that you should ignore here, but here you see we can make a color code with a hexagonal lattice. So the yellow dots here all are qubits, and these green ones are ancillary qubits that we use for measurements. But one can have a color code on a hexagonal lattice, and then these parity checks act on 6 qubits at a time. And this picture I actually just sort of took from a paper from 2024 from Lacroix et al. So this is one of the experiments in the Google Quantum AI group. And the title is Scaling and Logic in the Color Code on a Superconducting Quantum Processor. Right, so this is an experiment actually looking at this code and a few other things that I'll talk about and showing how well we can do this experimentally. Okay, so quantum error correction, after the first codes were invented by Steen and Shor, more larger family of codes were invented. But another question was immediately clear that we had to answer. We need fault tolerance. Okay, so what does this mean? The question is, so there's that sort of breaks down in 2 questions. Question 1 is, all right, so I said quantum error correction is about computing these parities. I have to measure the qubits. I have to measure like ZZ on some bunch of qubits. How am I doing this? I'm doing this with noisy components. But how can I be guaranteed that I'm not introducing more errors than I take away by doing this? So how I want to compute parities to learn about errors by interacting with the qubits, and through this, possibly introduce more errors than one takes away. This is highly non-trivial, right? I'm using noisy components in everything I do. So maybe by checking whether errors happen, I introduce more or take away. Error correction only makes life worse. So I need simple methods to kind of learn these parities. And this is where Kitaev came in. This is water, can I use? Yeah, so this is where an idea of Kitaev has been very influential, because he came up with the Tor code in '96, and that uses local verification. It means that the parity checks that you have to measure only act on a very few qubits, namely 4. And you can make the code larger, that's to say you use more and more qubits, and still these parity checks only act on 4 qubits. And if you make errors on them, they'll affect only at most those 4 qubits. So you're not going to generate a lot of errors, you're only going to generate sort of local errors. And that was not true for the Tor code initially, and that was a very crucial idea. The second question is, well, okay, so now maybe I've represented, my physical qubit by 9 qubits, that's 1 logical qubit, but now I want to do logical gates on it. I want to run a quantum computer on it. So how am I going to do that? How is one to compute on logical qubits in a way that does not spread errors in a bad way? Say that is fault tolerant. All right, just to understand what fault tolerance means, as an example. So some gates that I can do on an encoded qubit are transversal. For example, I have to do a controlled NOT, and I have 2 logical qubits. Originally, I had 2 physical qubits. I have to do a C0 between them. Now, each logical qubit is maybe 7 qubits. Here in this picture, there are 3. And of course, it would be nice if I could just interact, do this interaction 7 times, which, qubit number 1 here, and qubit number 1 there, and qubit number 2, and qubit number, etc. Why would this be nice? Is because, well, I can do all these gates in principle in parallel if my hardware allows that, because they act on different qubits. And secondly, in this block of 7 qubits, well, here there are 3, none of these qubits interacts, at least not according to the C0 logic. Because none of the qubits interacts, a single error that happens on 1 qubit should not spread to the other qubits in principle. A single error that happens here may spread to the other block. That's inevitable, because I have to do some logic, I have to entangle them. But it doesn't spread inside the block. So these are naturally transversal. It's naturally fault tolerant. But the problem is, and we know this now in a later theorem, that there is no code in which all these gates are transversal. It just doesn't exist. There are gates we'll always have to do that do not allow for this construction. And that's rather painful. And Shor actually very cleverly came up with a construction that's not his 95 paper, this is his 96 paper. He found solutions to 1 and 2 using fairly complicated constructions, but showing that fault tolerance is possible. So he found a complicated non-transversal construction for a Toffoli gate, which is fault tolerant. All right, but now I want to say something about Kitaev's idea, because that's overall been more successful, especially at this state in the lab. So what's Kitaev's Tor code? Now I sometimes call it the modern day Ising model, because it's such a well-studied model. And there's many generalizations also in coding theory land and so on. All right, well, I've already showed you this small stellar dodecahedron, so where also you present quantum error correction and topology. Okay, but let's take a torus, and we're going to just tile the surface of this torus like this, and on every on this tiling on every edge we'll put a qubit. And of course I could make a finer grid, or I could make a very coarse grid. If I make a finer grid, I'm going to create a code with more physical qubits. This code is going to encode 2 logical qubits. And the logical qubits will be associated with the 2 non-trivial loops around the torus, the red one and the blue one. All right, but now I have to specify what is this thing about local verification. Sorry, I have to specify what are my parity checks. So for every face of the lattice, this is a face, there is a face parity check, which acts like z, 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 z on all the qubits. So this parity check should have eigenvalue 1 if I'm in the code space. So if there is an error, particularly if there's an X error on any of these qubits, this eigenvalue will flip to -1, so if I measure it, I'll detect the error. Similarly, for every vertex, there is a X parity check. So there is X acts on all the edges coming out of, emanating from this vertex. And again, I have to measure this. And you see, as promised, I said for KT-TIFR code, these parity checks act only on 4 qubits. They're local, and so if I make this grid of, on this lattice very, very fine, then, that set of 4 qubits, if I make an error here, it stays very, very localized. All right, so this KT-TIFR code is this idea of that, topology allows you to sort of encode something, because, as I said, the logical operators are non-trivial loops. So they're loops of z's for the logical z, and there's an associated, so this is one logical z, and this is another logical z. And then there's also an associated logical x, and those are sort of loops on the dual lattice. If you go, if you map faces onto vertices and vertices onto faces in 2D, you go to the dual lattice. So this is a code that is distance d, and you pay for it by d squared physical qubits. So it's not very efficient in terms of like how much distance you get, meaning how many errors you can correct for how many physical qubits you use, but it has this local verification, which is very nice. And it also has a lot, it's very robust to noise, as we'll see in a moment. Okay, so now the question is, how do you measure these parity checks? And this is essentially what you have to do in the experiment, right? So these quantum error correction experiments has been done so far. You prepare all your qubits, maybe these squared qubits, all in 0, and then you start measuring the parity checks. And you do this over some time. So there are many cycles of measuring these parity checks. You measure all these parity checks, you record what you find, and then at the end you measure all the qubits. And then you have to determine, what's the state of the qubit, or what's the logical state. And for example, maybe initially, somebody else prepared all the qubits in all 0 or all 1, and you weren't told. And only on the basis of this whole record that you measured and this final measure, you have to determine whether it was a logical 0 or a logical 1. So that's sort of the idea. So here's the measuring the parity checks. So you use ancillary qubits, or sometimes called measure qubits by Google, actually. And so, for example, if we look at this circuit, this is a circuit to measure a z-check, and you can see here, so there are 4 input qubits, and if there's an X error on one of these qubits, that will propagate here. It will flip this control, and therefore it will flip this qubit. And then, if there's an even number of X errors, the parity is not flipped, so you flip, an even number of times, so you don't flip. If there's an odd number of flips, you flip in an odd way. So this is how you can understand that this measures a z-check. And for the X-checks, there's a similar measurement. But you need this ancilla, but you just need 1 qubit per parity check, which is very efficient because the Shor constructions had many more qubits. There's also a Steen construction, also has many more qubits to use. Okay, sorry. Okay. Now, the important thing about this fault tolerance is that there's 2 effects that you can sort of get from if you measure these parity checks. And the one effect is that errors feed back to the data qubits. And I said, well, they'll affect at most 4 qubits, but they will feed back. And the second thing is that due to errors in this circuit, you just don't get the right outcome. So the first example is here. There's an X error here, and it can feed back to 2 physical qubits there. But okay, so that maybe affects 2 qubits here, and you have to worry if the code can only correct a single qubit. But if the code is big enough, if the distance is large enough, you can correct this type of error. Now, one thing I want to say about this, and also about KT-TIFR code, this idea of local detection and these codes that have this property generally go under the name of LDPC code. So LDPC is a notion that comes from classical coding theory. It stands for low density parity check codes. And classically, these are the best codes that we have or used in wireless networks and so on. And these codes are sort of constructed from just taking subsets of bits and doing parity checks. And the size of these subsets of bits is just constant, like 4 or 10 or something like that. But it doesn't grow with the number of total bits that I have. And that's what this sort of low density means. And every bit participates also in sort of order 1, like 5 of these checks. And similarly for KT-TIFR code, you have parity checks of weight 4, and every qubit participates in 4 checks. So there's been generalization of the toric code to many overhead efficient quantum LDPC codes. This has been a very nice theoretical development since 2020. All right, now there's the second thing, is that, of course, there could be errors that sort of mess up this in this measurement or prior to this measurement. For example, there's a Z error here. Hadamard makes it an X error, and that flips the measurement. So what you do is that if you measure something, you shouldn't trust the outcome right away. You repeat the quantum error correction cycle. What else are you going to do? You know, if it detects errors, you're going to repeat this quantum error correction cycle. And then you're going to infer errors from multiple measurements. For example, if you get, if you get 3 of these measurements, you take sort of majority voting. Yeah, thanks. Oh, sorry. Yeah. All right, so now Kiteev's toric code had periodic boundaries. It was the tiling of a torus. So subsequent development was to a surface code. In the surface code, the pictures are slightly different. So just bear with me for the moment. Here, this is the smallest surface code. There are many color code variations. And the physical qubits, there are 9 physical qubits. They're in these red dots. And then there are these ancillary qubits that we need to measure the parity checks. For example, I need to measure an X parity checks on qubit number D1, D2, D4, and D5. And I need to measure a Z parity check here. And you see also on the boundaries, there's sort of these half parity checks that I need. So the lattice has to have a boundary. Sometimes this is also shown like this. And the logical operators, again, they stretch the size of this lattice. So this is a DS3 code because the logical Z goes like this. And this is a DS7 code because the logical Z goes like here and the logical X goes like that. All right, now let me say a few things about the surface code and color code and some pros and cons. So why have people focused on this toric code with boundaries, which is called the surface code? So this is Google's paper and some data. Well, they have planar chip. So if you put the ancilla qubits, they can put them on the plane next to the qubits of which they have to measure the parity checks. So that's nice. There's not too much overhead. So this is sort of their DS7 surface code picture. Another fact is that you can say, well, still, even though things are noisy, if they're too noisy, I'm still making things worse using error correction. And this is what's characterized by the threshold. So for example, in this experiment, they do repeated quantum error correction cycle, and they look at the logical error rate per QEC cycle. So for example, if you do repeated quantum error correction cycles, the logical error probability will go up, right? If it goes to a half, you don't know what state you have. You're completely lost. And it keeps going up, so you can extract some rate from this. And this rate should go like this. This is theory. So it should go down something like P divided by P threshold, and P is the physical error probability, to some power related to D. So if P is less than P threshold, this goes down exponentially. And this is exactly what they're seeing. So the point is, there are theory predictions and there's theory numerical modeling of this. And this theory numerical modeling, we get sort of the threshold is about 0.75%, but these are very simple models. So the question is, if you're on a chip, you have crosstalk, and you have varying error rates and so on, it's all different. Thank you. And so they see, and this is basically, this is a very big breakthrough because, if you see quantum error correction was invented in 95, we're 30 years later, and this is the first group that has shown to be below a threshold in the way really that you have more qubits, more redundancy, and your logical error rate goes down exponentially. All right, but there are some disadvantages to going strictly planar, and this relates to how you do logic. For example, I'm not going to go in this because I'm out of time. So if you have a strictly planar architecture, you have to do the C not in this nice transversal way, but in some other way that requires actually sort of a slowing down of logic. If it's transversal, it takes one time step. But in the way it has to be done on a purely 2D architecture, you have to use sort of order D QEC cycles to do this. And so it slows down the computation. And if you are, so for example, if you could sort of put these sheets on top of each other, and for example, in the neutral atom qubits, they can move qubits around. So they can sort of, they can take 2 color code qubits and move the qubits such that you can do gates transversally, then that can have advantages in terms of speed. Now, the fact that the clock cycle is much slower for these neutral atoms than for the superconducting qubits is a disadvantage, but beyond 2D connectivity has some advantages. All right, now there are other codes, there are other gates that you have to do, and here is where the color codes are actually shine, because what gates you have to do, for example, for universal, so if you want to build an arbitrary quantum circuit, we have to do the C0, we have to do a Hadamard, we have to do an S, we have to do a T. Now, the Hadamard, the S, and the C0, we can all do transversely for the color codes, and we can't do that all transversely for the surface codes. So the color codes have some advantages, but then there should be tricks. There's tricks to do the T gate, and the essential thing about the T gate is these tricks are harder, and what we want to do is we want to be able to do it without requiring lower physical error rates, right? So in order to do universal quantum computation, we'll have to implement these gates. But if doing these gates uses very complicated constructions that are prone to errors, we may have to start with even lower error rates than we have now in many physical experiments, and that will hamper progress. So we'd like to do it in a way that is not sort of the bottleneck in terms of the strength of the noise. And the method has been developed, it's called magic state distillation. And Lucan's group on the neutral atom has implemented this magic state distillation of neutral atom qubits on color codes, going from a DS3 to DS5 color codes. But they don't try yet to be below threshold for the color codes. And this is an important point. The neutral atom qubits are amazing in terms of what they've shown so far. But they have not shown something like the Google experiment on the superconducting qubit, where you really, you go to sort of larger code size and you do many cycles of error correction. And you show that the bigger the qubit is, the bigger the logical qubit is, the less error prone it is. Okay, so that's sort of my end of my talk. I think I'm out of time also. I want to say, so I haven't said anything about my work. And this is just sort of in the last slide here. So they have been more efficient. I've mentioned the overhead. So the surface code has large overhead. So people have looked at quantum LDPC codes with less overhead. So this is a paper in Nature that has 10 times fewer physical qubits to get sort of the same performance as the surface code. You can't do this with strictly 2D connectivity, right? But IBM has an idea how to build this in hardware. For this scheme, each qubit needs a C0 connectivity with 6 other qubits. And we have a scheme which actually has the same performance. We also have a new code. At least it's not any worse, and it only needs connectivity with 5 other qubits. And it uses some neat idea about dynamic codes. If you want to know more about it, you just ask me in the break. Okay, so that's finishing up here.
Are quantum error correcting codes in the present stage, are they information sensitive or signal sensitive? Like for which signal you are using quantum error correction code?
Well,
does it vary from signal to signal?
What do you mean signal?
Like as per my knowledge, quantum error correction you use for some kind of quantum communication, right?
Yeah,
it passes through some environment and then you try to correct it.
Yes. Yeah.
So does it depend on the origin?
Yeah, thank you. No. So they're not being used in this communication setting. The thing is, in communication, usually if you think about it classically, you say the channel is noisy, and then what I do at home, I do on a classical computer, and it's noiseless, right? But that's not the model we have in quantum computing. We don't have any computers. Everything we do is noisy. Yeah. So so now what the first thing that has been shown that in the lab, on some, on a device, I can use a quantum error correction code, and the more qubits I have, the better I can protect the qubits. But if I send, well, it depends on how noisy the channel is, then you could also in principle correct this. Yeah? But they haven't been used, there's not a clear example of where they've been used in transmission, but the problem is that the decoding, what you do after the transmission is also very noise prone. So you first have to show that you can do that. Does that answer your question?
Barbara, I mean, are you aware that people, I'm just asking whether, is it possible that you don't attach any ancillas and use some kind of random matrix models to do the error correction code? Has anybody used it? If yes, please tell me.
Well, okay. So the thing is that the ancillas are used because you need to extract information from the system. And if you start measuring your qubits that encode the information, you destroy their state. So you don't want to measure one qubit, but you want to, you want to learn information about the errors, right? And so that's why you use your ancillary qubits. It doesn't need to be qubit. There could also be some other way of coupling a bosonic mode or cavity mode to a system. It's just that you have to extract information out, from the system to the outside world, and it has to be carried by some degrees of freedom. Now, actually, in this paper, we actually have a sort of a different paradigm where we actually have a quantum error correction code, and then we use some what we call morphing transformations by reducing some qubits in these codes, using them to detect the errors on other qubits in the code. Okay, so that's maybe, that's a different scheme, but that's typically not used for our results. This is sort of very useful.
Any other questions at the back?
Yeah, it's a naive question. So I was just wondering, most of the errors you were concerned about are discrete errors, some kind of flip errors in X or Z directions. What about continuous errors, for example?
Yeah, thank you for the question, because I didn't allude to this. So the point is that was realized indeed in these early papers. So if I do an over rotation, I can, like say on a single qubit, and I can expand it in terms of the identity and say an X error. Say it's a rotation around the X error. So I have to do an amplitude. So usually the error model is I have an amplitude of a certain error or a probability. And so these codes can also correct those errors. This follows from the formalism, and that was shown in Shor in 95, that even, so the thing is, if you have a slight over rotation, and if you're going to measure this parity check, with high probability, you can find that there's no error. You kind of collapse that superposition of errors into no error, or there is an error, with probabilities corresponding to the amplitude at which it occurs. And does that answer your question? And the other thing is that you have, so for the single qubit, you have X errors and Z errors. If you can have X and Z errors, you can correct Y errors, because X and Z, the product is proportional to Y. And any Hermitian operator can be written as a linear combination of X, Y, and Z plus an identity. So this basically, that mathematically is the basis for, if you can correct X and Z errors, you're good.
Yeah. Anybody else?
Hi, Barbara. Here.
Yeah.
Hi. Thank you for the lovely talk. So I want to hear your comments in with respect to two different directions. One is if we change. So essentially, the way that that I'm seeing this is essentially error correction in the perspective of basically digital classical computing or digital quantum computing, right? If we change the perspective of our computational model to like lambda calculus or something else, right? In classical and quantum, I just wanted to, I wonder out loud to you, does this bring any paradigm shift in the way that people have thought about error correction in the past? Have there been kind of bad ideas that didn't work in classical, but that could work in quantum? And the other question I also wanted to just throw out for your consideration is, qubits to qubits, does that provide any sort of, again, paradigm shift in the way that some of these problems could be solved? Can transversality be solved by going from, let's say...
Sorry, your last question, what do you mean by qubits by qubits?
Qubits to qubits.
Oh, qubits, yeah, okay, so qubits, yes. Yeah, of course, the theory of quantum error correction has also been developed for qubits. It's just that, the amount of control you have on a qubit is already hard to get. If you just go to a qubit, it gets more complicated. So qubits are just the simplest,
Yeah, I've seen these generalizations of the XYZ, like the polymatrices and stuff.
Yeah, there's a qubit toric code. There's also an oscillator toric code, for example. And there are also ways of, using bosonic mode to encode qubits. So an oscillator has a lot of space. So you can say, okay, I can choose, like we heard about the transmon qubit, I can choose 0 and 1, the lowest two energy states as a qubit. But I can also use two other orthogonal states as a qubit, such that I'm better able to detect photon loss and correct for this. And that's been developed as well. Now, about your first question, yeah, I don't know much about this, but to me, everything at the end is just it's a computer and which is captured by a circuit model. Maybe this is too simplistic model, but I think the fundamental assumption about errors is that the probability for having k errors at the same time is like p to the k if the error for a single error scales like p. So there's an exponential suppression depending on the weight of the error. If this is not true, then error correction is a bit in trouble. which you see a little bit in like, well, not in trouble, but you know, in the Google experiments and early experiments, they suffered a bit from cosmic rays, which caused burst errors. So errors that affect many more qubits all of a sudden. And there you have to be careful that you can still correct for that, right? And I think that will be an ongoing story moving forward.
Okay, so I think we'll save the questions for the coffee break. Let's thank the speaker again.